Hello everybody, Adam Lusick here, and today we're going to be talking about context engineering. More specifically, we're going to be talking about how research has been trending towards allowing language models to actually operate and manage their own context. There have been some interesting shifts in the world of applied AI where we're considering context less from a retrieval standpoint and more from a navigation standpoint. We're seeing this with research like recursive language models, and applied more directly in places like coding agents such as Cursor Agent here, or Codex, or Claude Code. And these systems are all built with the intent to allow a language model to actually be able to operate and understand millions and millions of tokens of context without the confines and limitations of a language model's context window. The expectation then is that given this ability, a language model can then operate for longer periods of time on more complex tasks that require a much broader contextual understanding of information that it operates with. There have been some pretty clever advancements in the way that researchers and applied AI practitioners are thinking about context engineering and context delivery, so that's what we're going to go over today. Starting with a little bit of background as to what context engineering in this context actually means. When we consider the language model as the program that we are almost developing and creating, our main way of actually programming the language model, or our main lever of interaction with the language model, is the prompt that we send to it. Prompting in and of itself is really how we define a lot of the interaction and behavioral guidelines for the model to follow as it does its subsequent generation or takes some form of action. We generally refer to the act of actually crafting a prompt that is able to more accurately get your intended interaction style or behavior from the model as prompt engineering, where the end goal is to essentially engineer or create a prompt that is optimized towards whatever style you are trying to replicate. However, a prompt can only do so much to actually guide and affect a model. It also must, to some degree, understand the context in which it is operating within. Context here refers to any sort of external domain-specific knowledge that you would like to actually allow the language model to know and understand so that it can better operate on whatever task you are doing. For example, if you are making a language model-based chatbot assistant that is able to answer questions about a product of yours, you would want the language model to actually understand the context of the product or all of the specific details so that it can effectively do any of the assistance or question and answering. The problem to solve then is what of your context is actually relevant for the model to know, and how do you effectively deliver only the most relevant content to the model? Solving for this is really where the world of retrieval augmented generation, or more commonly referred to as RAG, popped up, where systems are designed to do both this retrieval and delivery to the model. It is unrealistic to assume that you'll be able to provide all of the context at once to a model, as often we have many more documents and many more relevant pieces of information than we are able to actually fit into the context window of a model. Thus, ways to store and then dynamically search over content to be delivered into the prompts of language models were developed. As of the time of recording this, two main techniques to do this context delivery have emerged dominant. The first is the more traditional vector-based similarity search, where what we do is rely on embedding models to then take documents and embed them or encode them into semantically rich vectors. Essentially, we're taking something like a PDF or a text document and capturing all of the meaning of that document into numbers. And if we repeat this encoding or embedding process across all of our documents into numbers, we can use some specialized technology like a vector database to store all of our documents and then actually compare the similarity between them. This allows us to do a fuzzy search called similarity search. Rather than relying on direct keywords or various other searching techniques, we actually are going to rely on machine learned embeddings in this embedding or encoding model to compare the meaning of queries and documents and find what might be most similar. To provide an example of how this might operate, if we consider our past idea of a product Q&A assistant, what you would do is take all of the documents about your product and encode them and embed them into this vector database. Then, when someone asks a question related to a part of that product, say maybe the setup part of the product, a search would be ran on the user's query in this vector database and pull out everything similar to the question being asked around setup. So the expectation is that then the parts of your product documentation that are about the setup would be retrieved, returned to the model as context, and then the model will take both the user's query as well as the context delivered by the vector database and generate an answer. The second technique that we have then is what I'm referring to as file system search, or you may see others reference things like file system based agent harnesses, and a lot of these do the same thing, which is treating knowledge bases like a literal computer file system. And the idea here is that rather than have some sort of specialized system that uses a different type of database and a different type of model, we can take inspiration from how we might interact with files and file systems in a terminal environment. To do this, language models are generally placed into a sandboxed shell and given the instructions and ability to execute different shell-based commands. Often these are file navigation and loading based commands like grep, ls, cat, cd, touch, and others, so that it can do some form of exploration and looking into the files themselves. This technique is also what we see commonly used in coding agents that allow these language models to actually operate over and search over large code bases to find specific parts. So it ultimately relies less on a retrieval system and more of giving the tools to navigate context and have that form of delivery to the model itself. But going back a little bit to our problem statement, why exactly are these retrieval and context delivery systems needed? The main reason for that is because of the limitations of the context window that we have. All of our operating and relevant context must fit within the confines and limitations of a model's provided context window. And this becomes increasingly difficult as runs extend and the context window is further exhausted. Anthropic encapsulates this very succinctly by saying the context window is a public good, where everything that you need to interact with and define the program of your language model must fit within the context window. This leads us to a fun applied AI optimization problem, where we hope to minimize the amount of tokens that are exhausted from the context window while maximizing the usefulness and relevance of what actually does make it through, which, in this case, is what we were referring to broadly as context engineering. Now, before we talk about the modern techniques of actually doing this context engineering, it's useful to know exactly why this is a problem in the first place. To understand that, we must look at what the context window is and why this limitation even exists. In practice, we understand the context window essentially as the amount of tokens that a language model can take as input, which guide its subsequent generation. We see this grow linearly as each turn progresses, and more context is added or different messages are added, and then re-ingested at each turn to provide a full conversation. Tokens here, of course, refer to the learned format of language that the models actually process, where when some string of text is input into the model, it is split into individual pieces, and they look a little bit closer to numbers since it needs to do a mathematical operations on these, and then the model itself also generates these numbers, which are turned back into text that you and I can read at the end. But a little bit more technically, the context window is very intertwined and connected to the transformer and self-attention mechanism of the current architecture of language models. As sequences are tokenized and input simultaneously into the model, every token is then attended to or understood by the model through this self-attention mechanism. This is what allows the language model to actually interpret and understand the different meanings of words as they relate to each other in a full sequence. This is how models are able to perform nuanced interpretations of the meanings of words within the context of everything around them, such as in the example of this sentence, I have no interest in hearing about the rising interest rate of the bank. Interest here refers to two different types of words, whereas just naively, if you took these words out independent of the context around them, they would be the same word. But one of the quirks of the attention mechanism is that it doesn't inherently take into consideration the order of these tokens. It computes based on what the tokens are and how they relate to each other, but not where they sit. More specifically, this is called permutation equivariance, but practically this means that we have to somehow inject order information to the language model through the attention mechanism. This is meant to assist the model in understanding not just how the words relate to each other, but also the structure of the language. This is important because the relationship not just between the words, but also where they sit structurally does and can affect the meaning of them. For somewhat of an example, we as people understand how the structure of language affects its meaning as we grow up and learn to communicate, read, and do everything with the language that we are familiar with. This means that for something like the English language, which we are operating within right now, we understand how things relate from left to right as we read it, as well as how the different pieces interact with each other as they are at more the beginning or the end of a full document. The model understands some of this as it starts to pick up and learn human language, but it must be assisted through actually injecting different positional understanding directly into the information that it's processing. Historically, we've seen absolute positional embeddings be utilized where a fixed size table of vectors, one for each position, one through your maximum sequence length n, would get added to each token embedding. These positional embeddings would then very literally inject that order information into the full encoded sequence that the language model is going to process, but it imposes a hard architectural context length limit. A model would understand order only up to that final length of the positions that you're providing in your table. So looking at an index of n plus 1, the model would literally have not even learned how to process that position and thus not understand it. And this is how initial maximum sequence lengths were determined. Essentially, it would be up to whatever position of tokens that you would support in your fixed sized table of positional embeddings. And while this does provide a very literal understanding of position to the language model, it does have a pretty strong limit. So what happened is rather than rely on absolute embeddings, we turn to more techniques that provide a learned relative positional embedding. One of the modern techniques that's still widely used for relative positional embeddings is ROPE, or rotary positional embeddings, or rotary positional encodings. ROPE here applies a position-dependent rotation to each of the token's representations within attention, which is a very abstract and somewhat difficult to grasp concept, so I'll try and break it down at a very high level here. As we went over earlier, the encoded vector representation of the information that's being passed through the model captures the semantic understanding of the words in a mathematical format. These vectors then also, very similar to vectors in physics, have a magnitude and a direction. ROPE applies a transformation of the direction of the vector while maintaining the magnitude, or how strong the embedding is. And the transformation and amount that this vector is quote-unquote rotated changes based on the position within the sequence. Intuitively, you can think that earlier positions here have smaller rotations while later positions have larger rotations. Applying these rotations is actually not detrimental because as the attention model computes how two tokens relate, the actual rotations that have happened to these vectors largely cancel out. What's left behind then is a signal that's dominated by their relative offset, or essentially the relative distance between those tokens. This means that the language model would then learn relative positional patterns rather than absolute. My example that I've written down here is that the model would learn essentially something like tokens 10 positions apart behave like X, so then the interpretation of two tokens 10 positions apart would remain consistent regardless of whether they're at position 1 and 10 or 1001 and 1010. This provides a lot of the positional understanding of how tokens relate without having the limitations of a predefined index. The biggest benefit then is that without this bottleneck, we can actually generalize sequence length understanding without explicitly identifying every single position that we have. As a note, this doesn't exactly solve positional understanding across long sequences. Language models, as they're trained, would still need to be provided examples of how to operate, interpret, and use long sequences. But all of these techniques have come together to allow language models to go from very small input sequences of things like 2048 tokens all the way up to upwards of 1 million tokens in context. But tying this back to our original point of context engineering, there are still 2 points that we must discuss. The first is what we've already talked a little bit about, that we often have more context than can fit within the context window, over a million tokens essentially, and a interesting limitation that's been noted through research and application that not all context is actually treated equally by the model, despite being in the context window or these claims of being able to support large context windows. To speak on the second point first, we've noticed what is referred to as context rot, essentially a decline in performance at a certain level of tokens where the language models don't effectively actually use or utilize the context that is being provided within their window. There's a great technical report here from Chroma that I'll leave in the description below that you should check out that goes deep into detail of this, but we'll talk a little bit about some of their findings. Specifically looking at this, we can see that as context windows are used and utilized, there's a general decline at around 100,000 tokens of performance and accuracy. This was discovered using a technique called needle in a haystack testing, where a single gold or correct answer is hidden among varying lengths of input sequences. Then what happens is the language model is asked questions that can only be answered with the specific information and context contained in the gold context. If the model does return an answer containing the context from that needle, the gold needle, then it is considered a success. And through this testing, they found that unfortunately the model is unable to actually find or reference a lot of that information directly in its context window as the context grows. And this is further exacerbated with the introduction of distractors, or context that is actually similar to the golden needle that is trying to be extracted. I found their point in testing about the distractors actually very interesting because as someone who does a lot of applied AI in their day-to-day job, I often work with data sets that have a lot of noise and a lot of distractions. Things like enterprise unstructured data sets tend to be very unstructured in and of the sense, noisy, and have a lot of related, similar yet nuanced information that needs to be interpreted with a broad understanding of the context that it is in. It would be incorrect to assume that we can rely fully on the intelligence and processing of a language model to actually cut through and make sense of that noise. From what I found, a lot of this is a result of this distractor concept that Chroma is suggesting, where the interpretation of similar yet different information that's been retrieved and processed together is less robust than when we have very clear, very delineated topics of conversation. This makes context engineering even more important, as language models must, in these different cases, have a very broad understanding of the context in which it operates to be able to do that processing and interpretation in an accurate and effective manner. But going back to the inconsistencies of how context is actually used within the window, we also see some things with positional biases, where a language model will better interpret and understand actual context that's at the beginning or the end of what is input in as a sequence and miss a lot of what is in the middle. This phenomenon has been coined lost in the middle. But what actually causes this degradation of performance? We don't 100% know. A few of the hypotheses around why might be something like the training data distribution. It's pretty difficult to actually provide a lot of concrete examples of how to use, manage, and interpret large context applications. Thus, it is underrepresented how to actually work on all of this long context tasks in the training examples that the language model sees as it undergoes its whole life cycle of being created. This propagates through as the language model being unable to most effectively utilize all of the context within its window. There's also some research that states that rope techniques can exhibit a long-range decay that biases attention towards nearer tokens as your context grows, and other things that say that softmax attention within the literal attention mechanism can also disproportionately allocate to early tokens and reduce effective mid-context retrieval directly from the context window. But overall, this is a developing space of research, and further hypotheses and tests would need to be ran to say conclusively what actually causes this context rot. But with this, we understand then what actually causes the context window to have a maximum length, and then also some of the limitations of how context windows are developed and interpreted today. Thus, we can understand the problem that we're trying to solve for as we work towards further improving our context engineering techniques. One other point of note that was out of the scope of this discussion is a lot of this is also constrained by the hardware and memory, or the VRAM and GPUs that we have, that need to process and do all these calculations. So there is a physical limit to, as we require a lot more hardware to interpret and run the calculations needed and load all of the context for longer interpretations. So with that, we must find acceptance with these limitations and work to define some elegant solutions that can actually operate within these confines. As we mentioned earlier, a lot of the initial solutions to solving this problem centered around the technique of RAG, or Retrieval Augmented Generation. This is, as a refresher, where we had documents, chunked them and embedded them into vector databases, and then relevant documents were retrieved and delivered into the context window via a semantic similarity calculation. A query will be input into the database, compared relative to all of the other documents, and then up to a certain similarity threshold, those documents were returned. Context management and context engineering in this RAG setup is framed essentially as a search and retrieval problem, positing the question, how do we get the right context into the context window? But what's been found is that actually scaling these RAG systems becomes a little complicated, as improving them is less of improving an AI system and more of actually optimizing a search engine. It's effective for very well-defined domains and well-delineated information, but it still decouples a lot of the interactions with the data and discovery and injection of the data from the actual operating of the AI model itself. More in line with this paradigm is, of course, the second technique that we discussed earlier with file systems. This technique essentially reframes context delivery as a navigation problem. This asks the question, not how do we get the right context into the window, but how do we let the model navigate context itself? This allows us to essentially bypass a lot of the different search systems like traditional databases would give us, and enable a language model itself to progressively discover the information that it needs to find. It can search, preview, open, and deem what context is relevant to answer the query at hand using its intelligence and reasoning skills. As a plus, we've also seen this become popular because a lot of these models have a lot of trained understanding of digital environments and programming. So if we provide a lot of the navigation and inspection capabilities within the right environment and tools for the model, it can actually orchestrate and run with this task very effectively. This also lets us put together large sets of information that can be searched over and discovered, rather than trying to fit everything in all at once, which is, of course, infeasible due to the context window. But hypothetically, if we have the right tools to actually filter out and retrieve and inspect the information, we can have a very large set of information that can be navigated across. This then shifts the context management responsibility from the developer over to the model, as the model is given the right tools to navigate and manage context itself. This idea has been more scientifically explored through the aforementioned paper Recursive Language Models by these wonderful researchers here, some of whom you may recognize from past research in things like DSPy or Colbert. But they refer to a lot of this language model-led context management using a code execution environment, and also, which we'll get into in a second here, the ability to call other language models in fresh context windows as recursive language models. As a direct quote, they claim that the RLM framework treats long prompts as part of an external environment and allows the large language model to programmatically examine, decompose, and recursively call itself over snippets of the prompt. In practice, this means that a prompt is essentially passed as a variable in a Python read, execute, and print loop environment, or REPL, to the language model. The model can then perform any sort of operation on that prompt as if it were any variable in Python. So it can orchestrate the whole interaction through writing and executing code. A little bit of metadata about the prompt, such as the actual length of the prompt, is passed along with instructions that encourage the language model to iteratively search and explore the prompt using the REPL environment very liberally. The recursive part of recursive language model comes from the ability of the language model to execute a LLM query function, where it can call a separate instance of itself to actually perform some sort of task. This separates out individual tasks into separate context windows that aren't in the primary RLM context, where what happens is all of this prompt will be sent to the language model, and then a language model that is essentially the same setup, but without the ability to call another language model itself, will return a final response back. This is then generally captured as a variable and can be used for any sort of downstream processing within the environment again. For those more familiar with the deep agents architecture, which I will put a link to the video here now, this is essentially a sub-agent. But ultimately, the cycle ends when the language model inputs a final var function with the final variable that contains its answer that it wants to return back. But this leads to some very interesting and unique results. The first of which is that this language model query function that they have can be used and orchestrated within code in effective and creative ways. So you can see that in the prompt, we have some examples of actually using this in for loops to call iteratively over sections of a book. And since the actual context and the prompt is stored in a variable, any sort of operation can be combined along with all of these language model queries, and all orchestrated via interestingly generated code, which leads to some unique ways of solving and managing the context in this manner. And in the end, they were able to prove that using this style of setup and harness on the model, the language model is able to actually understand and scale its understanding of content, far exceeding its context window, upwards of 10 million plus tokens from some of their experiments. An interesting side effect of this is that it's not just a harness and environment and tools that the language model can actually use. The way that this is set up as an environment with a verifiable task of long context question and answering means that it can be used in all sorts of downstream training for the model to actually learn more how to effectively do this context management. The authors of the paper did run some experiments using supervised fine-tuning on examples of effectively using the tool and effectively navigating long context, and did prove that through a little bit of combined training plus some of this harness, it's able to even further increase performance. And for the keen eye who heard something like verifiable reward and environment, Prime Intellect here also took a lot of this experiment and applied it into the field of reinforcement learning, or creating an RL environment with the harness and having a verifier of actually being able to complete the task. So we can use a little bit of supervised fine-tuning as well as reinforcement learning to really instill the understanding of context management using this tool directly into the model weights. But overall, I feel like RLMs offer a very compelling solution for context handling because it combines a lot of the pre-established techniques that we've seen of summarization and context folding with subagents, all while capitalizing and utilizing the already trained code understanding of language models. We already saw a lot of this behavior emerge as a result of coding agents be developed, so the formalization of this in a paper from these authors is much appreciated and good work. We can also take a look at some of the code that was used to actually implement this with the RLM library from the authors of the paper here. So I'll have this in the description below and you can give it a star. But let's actually take a look at this. I ran a quick example modified from the repo's existing examples that loads Pride and Prejudice, which is available freely through Project Gutenberg, and asks the RLM for every marriage proposal, who proposes to whom, what is the response, and what are the consequences of each. And we'll be using GPT 5.2 as our RLM here. We can inspect the actions being taken and the results using their built-in inspection tool here. So we see that the system prompt and everything is passed along to the model here with all the good examples. And then this is where we were referring to the metadata about the prompt. So our context is a string with 748,000 total characters. My prompt then asking about the marriage proposals in Pride and Prejudice is wrapped in a little bit of further instructions about the REPL environment. And we can see that the model's first response is to print a little bit of the context and confirm the length of it, which we see it gets back the header here of the book. And with this initial understanding, we can see it start to iteratively interact with the prompt and context using the REPL environment. So it actually splits the book into 90,000 character chunks and then kicks off 9 subagent calls for each chunk, which it splits into 9 here, with an additional prompt instructing the sub LLM to do this extraction of any of the marriage proposals. We see all of these run and we get back all of the different responses from the subagents. Interestingly, it has a couple of verification calls to sub LLMs after this initial extraction, with one that's meant to aggregate and deduplicate, and then one that's meant to sanity check, before finally calling its 12th language model to provide the final answer. Whereas the RLM's final action, it puts in the final answer variable that is generated from the sub call all the way down here. We can see it saved as final answer and spits that back out to the user. So you can see how the RLM is able to effectively navigate and interpret the actual content here without fully having all of the contents loaded at once, and being able to delegate and delineate tasks into fresh context windows with sub LLM calls that come back with only the most pertinent information to orchestrate the whole system. Pretty neat. So with all this, I wanted to give a little bit of my closing thoughts of what I see in practice with RLMs versus RAG versus all of these different techniques. Essentially, we see what has become a trade-off between latency and accuracy, where we can use traditional RAG and similarity-based retrieval for a simplified, quick context search and delivery, while the more recursive language model side and related deep agent frameworks trade a lot of that speed for increasing inference time compute, widening the search and exploration to better understand and process the context needed. So in situations where your analysis can be a lot more long-running and contextual and speed isn't a limiting factor, then an RLM style framework is the way to go. But on the flip side, for other scenarios like chatbots, where something like latency plays a huge factor into user experience, then maybe the faster and narrower retrieval will be better suited for your use case. As always, what you should do is try both and test and see how your product reacts and the users react. But with that, I hope today we've been able to demonstrate and learn a little bit about what the context window is, the importance that it plays with prompt engineering and then context engineering, as well as some of the modern techniques and research that are being applied right now to allow context engineering to be more intrinsically closer to the language model. So if you like the video, like the video. If you have any questions, leave them in the comments below. And if you want to see more like this, consider subscribing. Thank you and have a great day.